0-point energy. Consider a particle with mass m moving in a potential U is equal to 1/2 kx squared as in a mass spring system. The total energy of the particle is E is equal to p squared over 2m kinetic term plus 1/2 kx squared potential energy term. Assume that P and X are approximately related by the Heisenberg uncertainty principle, so P times X is approximately equal to Planck's constant. Part A, calculate the minimum possible value of the energy E and the value of X that gives this minimum energy. This lowest possible energy, which is not zero, is called the 0-point energy. Part B, for the X calculated in Part A, what is the ratio of the kinetic to potential energy of the particle? Okay, so the energy of this particle, which is in the potential of a harmonic oscillator, p squared over 2m is its kinetic energy plus 1 over 2 kx squared is the potential energy, and we have P and X related by Heisenberg's uncertainty principle. P times X is approximately equal to H. So we can write for the total energy, P is equal to H divided by X. So let's substitute that here. H squared divided by 2mx squared plus 1 over 2 kx squared. So the energy has been written as a function of x. Now we want to minimize the energy. So dE dx, the derivative of the energy to find the extremum point at a certain x value, x0, is equal to 0 to find the minimum here. So if I take a derivative of this with respect to x, I will obtain x to the minus 2 derivative is minus 2 times x to the minus 3. So this will give me minus 2 h squared divided by 2m x cubed. And the derivative of 1/2 kx squared gives me 2 over 2 kx, so it's plus kx. Evaluated at x0 should be equal to 0 for the extremum point. So if I substitute x equals x0 here, I will obtain, because these 2's will cancel out, I will obtain minus h squared divided by mx0 cube is equal to minus kx0. The minus signs cancel. So you can see here, if I take this to the right hand side, x0 to the fourth power is equal to h squared divided by mk. So we can find x0 that gives the minimum energy to be h squared divided by mk parentheses to the power 1 over 4. Okay, so that's the x value which gives the minimum energy. Now part A, we were also asked to find what's the minimum energy. The minimum energy is h squared over 2m x0 squared. So we're substituting for x0 plus 1 over 2 k x0 squared. So substituting for x0 squared, h squared over mk to the power 1/2, we have h squared divided by 2m x0 squared is h divided by square root mk plus 1 over 2k 1 over 2k x0 squared is h divided by square root mk. So this will give us a minimum energy now you can see here we have m and square root m. So this is going to become square root m on top. So let's cancel out one of the h's. So we will have h over 2 h over 2 square root mk over m will give us square root k over m. K over m square root. That's the first term. And here we have also k divided by square root mk, which is square root k over m. So this is also h over 2 square root k over m, the same term. So basically this is multiplied by 2. So this gives us the minimum energy of this particle to be h square root k over m. That's the minimum energy. So this is called the 0-point energy. Now, when it has this energy, what's the ratio of the kinetic energy to potential energy? So the kinetic energy is h squared divided by 2m x0 squared. Potential energy is 1 over 2 k x0 squared. And when we take the ratio k divided by p, we have h squared over 2m x0 squared divided by 2 over k x0 squared, which is h squared. Let's see the cancellation of 2's here, divided by km x0 to the 4th power. Now, x0 to the 4th power is equal to h squared over mk. You can see here, if I substitute h squared over mk, I will find that this is equal to 1. So I can say that the ratio of the kinetic energy to potential energy when I'm at the minimum energy, x is equal to x0, is equal to 1. That's basically what I have found here. Actually, these two terms were equal, so this ratio should be equal to 1. Okay, so we have a particle with mass m moving in the harmonic oscillator potential, and it has its total energy, and the momentum and the position are related by Heisenberg's relationship, uncertainty principle, p times x is equal to h. What is the minimum energy of the particle, and what is the value of position that gives this minimum energy? So we have substituted for p h over x into the energy relationship, take a derivative with respect to x, evaluate it at x0, set equal to 0 to find the extremum point, and we have found the minimum energy position, h squared over mk to the power 1/4. When we substitute this into the energy equation, we find that the minimum energy is h squared root k over m, and furthermore, we find that the kinetic energy and potential energy contributions are both equal to 1 over 2 multiplied by h square root k over m. So they have the same contribution, so that the kinetic energy to potential energy ratio is equal to 1.